This conference will now be recorded.
Okay, I'm going to go ahead and get started. My name is Doug Maddox. I have been working for the past few years, for those of you who weren't here last week, doing development and testing of eQuest and DOE23. And this week we're going to talk about dedicated outside air systems and series plant features. Last week's seminar was recorded, and I've posted both the recording and a PDF of the slides on my website at the address you see here, the improved sizing features. This week we'll talk about dedicated outside air systems, series chillers, boilers, towers, and next week will be variable refrigerant flow systems. And down the road, possibly, there will be future seminars on some of these other topics. So most of the talk today is going to be about the dedicated outside air systems, and then just a few slides on the series plant. Talk about what DOAS means and how it's implemented in DOE23, and give several examples of both input code and some results from those examples. And then finally, talk about the eQuest interface and the series plant. We're just going to kind of introduce the concept there and show some input examples for that as well. And today's talk will be a bit shorter than yesterday, so there'll be more time for questions and probably finish a little early. So basic concepts of dedicated outside air system involves a separate air handler, shown here as the DOAS, that both delivers and returns outside air from the either individual air handlers, as shown in the air handler 1 and air handler 2 here, or it can also deliver directly to the zone. So it can deliver air into the air handler unit itself or into the zone. And it's configured as a variable volume system, normally operates as a variable volume system in order to be able to accommodate the cycling on and off of different air handlers, or scheduling on and off of different air handlers, and also various outdoor air control mechanisms that might be handled. So as far as the features inside the DOAS unit, there's quite a few different options in this new DOE23 release. And basically, you can have a preheat coil, there's an energy recovery unit capability, cooling coil, heating coil, and dehumidifier. So it can do combinations of heat recovery, cooling, dehumidification, and humidification. And I'll give some examples of how that is set up and controlled in the models. So the basic implementation in DOE23, so for people who weren't at last week's talk, the first group of slides is going to be kind of focused on the language of DOE23 instead of the language of eQuest. And then at the end, I'll show how that translates into eQuest interface and give you a way to kind of cross-reference the two at the very end. So these next few slides will be using the DOE23 language, so hopefully that's comfortable for most people. So a project in DOE23 can have multiple DOAS systems defined, and each DOAS is created in the model as a separate system component. So it uses the same system features as other systems in the model, but the type that you define for dedicated outside air is DOAS. Okay, sorry, somebody came on unmuted, so I just muted everybody. Hopefully that's not a problem. So the DOAS system has many of the same keywords as other system types, and such as a heat source, cool source, min supply T, max supply T. So there are lots of overlapping features that a DOAS system has compared to conventional air handler systems defined in DOE2. So you define a DOAS, and then one or more systems, usually multiple systems, would be attached to the DOAS as being the systems that are served by it. And that is done by in the served system, there's a keyword called DOA-system that you assign the name of the DOAS that serves it. And then you tell it how the outside air is delivered by the DOAS to the served system. So it's either delivered into the mixed air chamber in the air handler itself, or it can be delivered directly to the condition zones on that system. And one point to note is that economizer is not allowed for systems that are attached to the DOAS. And I know some people have expressed that that's kind of a problem for some of the designs that they run into, but that's the way the current system is set up. So there's one of the keywords that is common to DOAS and other system types is fan schedule, and it's acceptable to not specify a fan schedule for a DOAS, and if no schedule is specified, the DOAS will operate anytime any of the attached systems has a fan schedule of 1. So if any single one attached system is scheduled on, then the DOAS fan will operate. And it will not operate during night cycling. So if all of the served systems are in night cycling, then the DOAS will be shut down. It is, as an alternative control strategy, you can actually specify a fan schedule for the DOAS itself. And if it has a value of 1, then the DOAS will supply, depending on how it's attached to the zone, to the served systems. If it's supplied to the mixed air, then outside air will only be delivered to that system if the fan of that system is enabled, and that is including a night cycling. If the DOAS is supplying to the zone, then outside air to that system will be delivered even if the fan of that system is scheduled off. So that's a little different logic than if you're defaulting the DOAS schedule to the served system schedules. And then if the DOAS has its own fan schedule and this value is 0, then that unit is forced off and it won't deliver air to any of the attached systems or zones, no matter what they're calling for. This is a little just discussion of temperature set points for the DOAS system and the defaults that are set automatically in the program. And I found this to be a little confusing when I started working with it. And there's basically the logic is if you specify, there is no default for the min supply T, so you're required to set something for that as long as there's heating or cooling delivered by the system. And then the defaults for max supply T and the cool set T and heat set T are based on the min supply T. And they may not always be what you intuitively expect them to be. So and the thing that tripped me up when I was doing this is that the max supply T is defaulting based on the min supply. It's not defaulting based on the heat set T. So my recommendation is don't use the defaults for any of those, just to specify all 4 of those values, and you won't get unexpected results. Okay, now I have 8 different sample runs or sample scenarios I looked at. So there are actually 9 runs, even though it only numbers to 7. 3 has an A and a B, and there's a 0, which is the baseline case with no DOAS. So I'm going to go through all of these. I'll go ahead and just read through this list and describe them, and then I'm going to go through in detail what the input code for each of these looks like. So again, the 0 case is no DOAS system. The number 1 case is a DOAS with no conditioning. So there's no heating or cooling coil or heat recovery in it. It's just got a pair of fans to blow air in and out of the building. Number 2 case is dehumidification. So now there's a cooling coil with room neutral cooling. And I'll explain with some numbers what that room neutral cooling means in a little bit to be more clear. The next case is dehumidification with room neutral cooling and heating. So I've added heating to item number 2. In the first 3 cases, I'm delivering air directly to the zones. And then for this 3B, the only change I'm making is to deliver to the mixed air, and then instead of directly to the zones, just to kind of show for this example what impact that has. And number 4 is a modification of 3A, but we're preconditioning the air differently. So I guess I can just explain. Room neutral is kind of what would be comfortable for an occupant, whereas in this case, it's preconditioning to what an air handler might deliver of 55 to 70 degrees air. Number 4 again or number 5 is like number 4, but we're removing this explicit dehumidification. So it still has heating and cooling, but it's not controlling to a humidity set point. Number 6 is going back to the nominal, or nominal preconditioning. So it's this 55 to 70, but with adding an energy recovery ventilator. And then 6 is, the final one is like number 6, but a room neutral temperature delivery. Okay, so number 1, the fan only example. Again, there's no heating or cooling. So you have some fan energy consumption, and the motor from the fan and the fan itself adds a certain amount of heat to the air. And for the model that I'm testing this with, I'm delivering the air directly to the zones. So it's a fairly simple input for this case. I define a DOAS system. The type is DOAS. Heat source is none, cool source is none, and then there's some fan power defined. There's different ways you can define the fan power, but I'm just doing it kind of in a simplistic way here. And then the systems that receive the air have 2 keywords defined that I showed earlier that relate to, it specifies DOAS1 as the system that's providing the air, and then another keyword that tells it that air is going directly to the zones. Case number 2, we're dehumidifying the air to room neutral. So everything that's red is a change from the previous case. And I've got some comments off on the right. This supplier temperature kind of ranges from 70 to 75 if there's any call for cooling. And one thing to point out here that's kind of important is that there's not a single control point that's related to a zone, because you're not there's not a control to a single zone or a single system. So the control of humidity is controlling to the supplier dew point. That's how the DOAS system is configured for DOE2. I think that's maybe kind of a typical control in the industry. So that's a different way of looking at humidity control than what we've seen in the previous DOE2, and something that differentiates the DOAS from other system types. Another thing to point out here is I've got this max con recovery. So I'm recovering heat from the DX condenser and adding it back into the airstream as reheat. So it's doing kind of a heat recovery from the condenser in order to reheat the air back to this 70-degree set point. As far as the temperature control, it's being using a constant temperature control strategy. And I bumped up the fan power a little bit in this example compared to the previous one to account for the static pressure across the coils. So the next example is adding just a heat source, which I'm modeling as a furnace with a 80% efficiency. And again, in 3, I have the 3A where it's attaching to the conditioned zones. And then I've got this 3B where I'm attaching and delivering air to the mixed air chamber of the attached systems. Case number 4, we're instead of shooting for a 70 to 75 degree air temperature delivered to the systems or zones, I'm now broadening that to 55 to 70. So that's the only difference between this and the previous case. And this one, I'm taking away the explicit dehumidification. So I'm taking away this keyword that says max dew point equals 55 and taking away the condenser recovery and the set point that's related to the max dew point. And now I'm adding energy recovery. And all of these keywords are new compared to the previous input. And the final case is energy recovery again, but just having the air tempered to be kind of a room neutral delivery temperature range instead of 55 to 70. So here's a busy table with all the results from all those runs, and I'm going to spend a few minutes going through this, but we'll just go one line at a time to make it absorbable. So don't try to look at all at once. So the first case, 0, is our baseline with no dedicated outside air system. And the delivery method, these first few columns here are kind of the input parameters that doesn't really applicable delivery method to the zones. It should have been just NA. So all these things are NA because there's no DOAS. So we've got fan energy, this is annual energy, cooling annual energy, and heating annual energy. So then the first DOAS case is unconditioned. So there's no heating or cooling set point. Delivery of the air is to the zones, and then there's this relatively smaller fan power of 0.25 watts per CFM. So you can see you're adding fan power, and the fan power puts some heat into the airstream, so it increases your cooling somewhat and decreases your heating. So in the second scenario, now we're adding some actual conditioning in the DOAS, dehumidifying and cooling to a room neutral condition. So the cooling set point 75, and then the dew point set point 55. Again, the fan power goes up a little bit due to the coils. And one thing that kind of surprised me, I'm afraid I just accidentally clicked my screen, so it's okay, we're safe. I didn't realize I could hold the button down and it turns into a laser. So the cooling goes down when we've added some cooling, or the fans go down, I'm sorry, when we've added this cooling capacity to the DOAS. And I kind of dug in, I didn't really expect that, but when I dug into the model to understand what was going on, what I discovered was that because there's cooling delivered by the outside air unit, there's a smaller cooling load in the units that are served by it. And it was a result of that, the downsizing of those units. So I was auto-sizing this. It was able to, the fans were also downsized in that particular case because of the way the fan sizing was set up. And so the fan power went down, and the cooling, however, increases because we're doing cooling in the DOAS, and sometimes that cooling is actually not useful out at the zones. So we have to it's providing cooling that's not helpful, and it ends up kind of providing doing cooling when it's not needed. So overall, it's redundant, and the net cooling for the building goes up, and heating also goes up somewhat because of that same issue. So the next case, we're adding heating to the DOAS and providing higher overall temperature. So you see a fairly big jump in the heating energy, whereas cooling, there's also a somewhat of an increase in cooling for the same reason. We're providing heating sometimes from the DOAS when it's not needed, so you end up having to do cooling out at the delivered systems. And then this next case, 3B, we're delivering to the mixed air instead of directly to the zones. Everything else is the same about that one. Not a big difference in the results, a little bit increase in fans and cooling and a little bit decrease in heating. And I think that's because we've got more air going through those individual systems that are served. So that's increasing the energy used due to that higher airflow through those systems. The next case, we're instead of delivering the 70 to 75 degree air from the DOAS, we're delivering a broader range of 55 to 70. And as a result, there's less excessive overcooling or overheating by the DOAS. And you see all of the end uses go down, fans, cooling, and heating are decreased somewhat by that. In the next case, we've removed the dehumidification. We still are doing the 55 to 70 delivery of air temperature, but we're not explicitly dehumidifying. So the biggest thing that I found there is that you lose a lot of that benefit of the sizing that we had back in that first round where we were downsizing the fans. So the fan power goes up quite a bit, and cooling and heating go down somewhat. The next step is adding the energy recovery, and the fan power is increased because of the heat, the resistance of airflow resistance of the heat recovery media. And so the fan energy is going up a little bit, cooling is going down slightly because it's an enthalpy recovery wheel, and heating goes down significantly. The climate is Chicago, so it's a fairly cold climate, and significant heating benefit. And then the last scenario here, we're changing instead of the 55 to 70 temperature range, we're going to the 70 to 75 temperature range. And again, there's increase in fan energy, decrease in heating, and an increase in cooling because we're generally delivering air that's over conditioned. Kevin asked a question what the indoor fan mode is for the zone units. So the indoor fan mode would be continuous in these scenarios. Okay, so and it's a lot of information, but I just wanted to part of my goal here was to provide examples of how the DOAS could be configured, so you have some code examples to look at if you're using this in your own projects. And so I want to look at a bunch of different scenarios, and I wanted to run them just to make sure they worked and that they gave meaningful results. So that's why there's all this data, because I wanted to review it and make sure it all made sense before I shared the code input examples. But I guess I found the results to be interesting. So hopefully that, even though it's kind of an overload of information, hopefully some people found it interesting as well. One final topic related to the DOAS is for demand-controlled ventilation. Just want to talk a little bit about how the DOAS interacts with demand-controlled ventilation. And again, with that same model, I did some testing just to kind of see how things work and make sure they worked. because this is, new features that we haven't really tested out in a lot of projects yet. But so basically the DOAS supply, if you have it configured where the DOAS is supplying directly to the zones, then if you have a demand controlled ventilation, it behaves as though each zone has its own CO2 sensor, and then it controls the airflow to that zone based on the signal of that CO2 sensor. So it's, and in the model, that's based on the hourly schedule of occupancy of that zone. And it's kind of going to give equal or less outside air to what you would get as a requirement using the ASHRAE critical zone method. That's kind of something I looked into and concluded when I was kind of figuring how this all works. Another thing that kind of surprised me, but made sense once I looked at it, was that at least in an office building, the demand controlled ventilation with the DOAS tends to increase your cooling load. And the reason for that is when you have DOAS, there's no ability to have an economizer. So if the demand control ventilation is reducing the outside air, and there are potentially significant times when the system actually wants that outside air in order to provide free cooling. So you end up with some increases in cooling energy as a result of that. So depending on your climate, you may find that demand control ventilation for a DOAS system where there's no economizer override, then there's an energy penalty. The other scenario, if the DOAS is supplying it to the mixed air, it's the control as if there's a CO2 sensor in the mixed air chamber of the receiving air handler, and it ends up being fairly similar energy results and performance as if you didn't have a DOAS, if the DCV was being controlled in a mixed air without a DOAS system. So it's found those results to be fairly similar. That makes sense. So I've got a few slides here showing how the DOAS is created and adjusted inside eQuest. So you would create the DOAS as you would any other system in the detailed edit mode. So you go in the menu and choose create HVAC system. And once you create the HVAC system, you give it an appropriate name. And in the system type, you would select DOAS. And then it will come back and ask you if you want to assign a heat source, and you can have it be none, or it could be any other typical available heat source, and same for the cool source. And then in the detailed interface, once you've created the system, you can go in, and the interface is fairly similar to other HVAC system types. One difference you can see off on the right is with humidity control, the max humidity and min humidity are grayed out. However, the maximum dew point and minimum dew point are allowed to enter values. I'm not sure if you enter a number in for maximum dew point. I think it should hopefully ungray out humidifier type, because you should be able to specify the type of humidifier. So hopefully that's working. You can't tell from that screen. And then this is the system that gets served by the DOAS. And there's just the two keywords. You select the name of the DOAS system, and this would give you a list of all the DOAS systems that you've created for your project. And then you tell whether it's attached to either, or delivering to either the condition zones or the mixed air section. And the example that I showed, case one, where we had dehumidification with a specified dew point, and I had condenser heat recovery into the air to provide reheat. I discovered that it's not super easy to find where you specify that condenser heat recovery. So I just highlighted that here in this presentation so that people can find that. So you go to the heating tab of the DOAS system, and then this cap curves waste heat subtab, and then there's this max con recovery for specific heat. So you specify the ratio of the condenser rejection that can be used for heat recovery. So that's all I had for the DOAS, and then move on now to series plant equipment. So just an introduction of what it means, and for people out there who aren't familiar with series plant, basically you have a loop with plant components that are one after another in the loop, so the downstream upstream relationship. And the capabilities in DOE2 only allow an upstream and a downstream. You can have two positions in the series. You couldn't have a third one downstream of that. And the thing to know that can be tricky in how this works out is that the entire flow passes through both chillers. And I'll talk more about what that ends up meaning in the simulation and energy use. It is possible to have different size chillers. The upstream and downstream can be different sizes from each other. You can have more chillers than two, but as long as you just have an upstream and a downstream position. So you can have multiple chillers, or whatever the plant component is, upstream in parallel, and then downstream another bank of components. And the maximum limit of the chillers in a system would be 10. I assume that boilers would have the same limits, but I'm not absolutely sure about that. The upstream and downstream group could have different numbers. So you might have 4 in the upstream and 2 in the downstream. That's a flexible variable. So one thing that as I've worked with the series capabilities in DOE2 that has given me some trouble, and that I've found that you need to be careful about, is how the flow rates get sized. And in a parallel flow arrangement, you've got a temperature drop that typically would be about 10 degrees for a chiller, which corresponds to about 2.4 GPM per ton. In a series arrangement, you would typically have those same values for the whole chiller plant. So if you have the upstream and the downstream, the overall delta T from the inlet of the first one to the outlet of the second one would be 10 degrees. So if these are equally sized chillers, then that means the delta T across the first one is 5, and then the additional delta T across the second one is 5. And similarly, you have much higher GPM per ton through each of those chillers. So there's a potential issue of pumping energy if you're pushing a lot of water per ton through the chillers, and so that's something that you need to pay attention to in your input and your output. I would recommend looking at the output results and notice what the head values are, the pressure drop in the pumping loops, to make sure that they're reasonable once you've done the simulation. So here's an example of input for a series chiller plant. It's really fairly simple. In the primary loop, you specify the equipment configuration to be in series, and then if you're doing automatic sizing, you specify a split of the capacity between the upstream and downstream. And then for each chiller, you then specify where it is located. So here I have a case where there's one upstream chiller and one downstream chiller. So chiller 1, I have the chilled water series location as upstream, and the downstream is downstream. These shouldn't have double quotes on them. That's kind of an error in my presentation material here, based on the source that I had it from was a set up, oops, I'm sorry. They were set up as keyword expressions, so they had double quotes for the expressions. And again, notice that I have the delta T set as 5 for the individual chiller, where the delta T for the overall loop is 10. And I found that if I let this delta T of the individual chiller default, that it works fine. The program, it knows that it should change the delta T for the individual chillers based on the fact that they're in a series arrangement. But if you don't let it default, if you put in a manual value that's 10, then you're going to get oversized or undersized system or flow rates through that chiller. So on to the eQuest interface. This is the primary chilled water loop, and there's a keyword here, equipment config, where you choose series or parallel. It'll default, I believe, to parallel, and then it will come back and ask you what the downstream split should be. And if you haven't defined the upstream downstream series location keywords for the individual chillers, it will prompt you for those values, and you select which one's up and which one's down. So this is my last slide. This is just a repeat of one I had in the previous presentation. Since I have again been talking in the language of DOE2 and DOE2 keywords, that doesn't always translate exactly to the language that's in eQuest. But if you follow this process and look in this BDL dialogues.txt file, you can search that and find where the keyword is in the eQuest interface. I tried to cover all the important keywords in the presentation, but it's possible I missed something. And that is the end. If there are any questions, I'd be happy to try to answer them. You can feel free to send a question in the chat box if that's, or you can unmute yourself if you want to talk. Okay, if there's no questions, I'll go ahead and close the presentation, and next week we'll be talking about variable refrigerant flow, and I think that one will be a little closer to the full hour. There's quite a few more slides in that one, so hope everyone found this useful. Goodbye.